last week's Scotland session, Tilings and Patterns. My name is Charlotte Webb and I'm joined by lecturer Reem Yasawari as well. And we are going to be talking to you today about both periodic and aperiodic tilings. So welcome. Do say hello in the chat. Let us know where you're coming from.
Hello, everyone.
Today.
Okay. So what we're going to do is Charlotte and I are going to talk a little. I'm going to talk a bit about crystals, about patterns in nature, about lattices. Then Charlotte's going to talk about tessellations. Then we'll go back and talk about aperiodic tilings. Tilings is just another word for tessellations. So I hope you enjoy this and you'll get something out of it, no matter what it is. So let me begin. Okay. So one of the things that mathematicians like to do is take simple words that we know the meaning of, whose meaning we know, and then sort of describe them mathematically. Okay, so one of the words that we like to describe, we like to define is the word order. So I'm going to ask you, think a little about what does it mean to be ordered? And it turns out that tessellations, regular tessellations, are what are called ordered structures. And the aperiodic structures we're going to see are in fact sort of what are called aperiodic ordered structures. Okay, so this is a picture and there's a little bit of order at the forefront. So we all know what that means. This is a crystal and crystals have lots of order in them. And that's what we're going to talk about for the first 10 minutes. All right. So this is a cave somewhere in Mexico. These are mammoth crystals. So you can see the man at the bottom right-hand corner is an actual real man. So these are really huge crystals in a cave, all right? Here's another crystal. So this is a zoomed in magnified photo of a salt crystal. So you have that on your food all the time, okay? And I want you to begin thinking, what are the words you would use to describe that object with, right? I've called it a crystal, but you might use some words so you can think about that, okay? You could even put them in the chat if you like. Here's another crystal. This one is a snowflake, right? So it's a microscope photo of a snowflake. And once again, there are words that might be appealing to you at this point. You might be using certain words. I don't know if the word ordered comes to mind, right? Or possibly the word structured, or possibly the word symmetry. So ask yourself, what kind of symmetries does this picture have? So you could maybe rotate it by 60 degrees because it looks like it's a hexagon. You could maybe reflect it along one of the axes. There are several of them, right? So that's kind of sixfold, periodic. Here's another crystal. So this is a crystal which isn't transparent. It's not see-through. So it's quite solid. So this is called fool's gold, right? Once again, it looks quite cuboidal, right? It seems to have some kind of symmetry. The face is a really smooth and shiny. This one is an emerald. So you might be lucky enough to have this hanging around at home, but maybe not the way it looks. So it's a prism. It's got a hexagonal face, right? So once again, you can imagine rotating it, and that prism would remain fixed under rotation by 60 degrees. Okay, you could even reflect it along a line of symmetry or a plane of symmetry, and it would remain unchanged. So I've been using the word symmetry a lot, but what you should think about, other than the fact that you can visualize it, right, is it's some kind of operation that when you perform it, the crystal doesn't actually change. The crystal is fixed. Okay, here's the last one. This is a diamond. This is not the last one, it's the penultimate one. Okay, so clearly has some kind of symmetry. All right, got those nice smooth faces. And this is a man-made crystal. All right, so humans can make crystals by taking, in this case, silicone and actually heating it up and then and then cooling it really quickly so that the atoms are really, really structured. Okay, so really crystal-like. All right, and if there's a tiny piece of that in the computer that you're looking at me through and that I'm looking at you through, except for I can't see you, but anyhow, it's thanks to this crystal that we're actually having this conversation today. Okay, so what is a crystal? I've been talking about crystal this, crystal that, okay? So what we've been discussing right now are what are called the macroscopic features. So the word macroscopic means that we can see these features with our naked eye, right? We've been talking about symmetry. We've been talking about how smooth the faces are, how structured it all looks. So those are macroscopic features. But these arise because of microscopic features, so tiny features that you can't actually see with the naked eye, all right, but which exist nevertheless. And it's the way the atoms are arranged, and they're arranged in what's called a crystal lattice, okay? So chemists talk about crystal lattices, and mathematicians were like, okay, what is a crystal lattice, okay? So let's talk about what is a lattice. So this is a lattice, so you'll say to me, well, I know what a lattice is, and that's exactly a lattice. It's a three-dimensional lattice because it lives in space, all right? The little green spheres are some atom, it could be chlorine, right? And the little gray spheres are another atom, all right? And that could be sodium, so this could be salt, sodium chloride, one atom of sodium followed by one atom of chlorine, all right? But mathematicians don't look at the baubles, at least not to begin with, okay? They just look at the lattice structure, right? And this looks like a cuboidal lattice structure. And if a crystal had that lattice structure, it would maybe have cuboidal symmetry, right? Which I really encourage you to think about. In fact, the cube, just the unit cube, you can get one, you can make one, and ask yourself what kind of symmetries are there, and you'll find out that there's sort of twofold, threefold, fourfold symmetry in the cube. So that's an exercise for you. All right, so mathematicians begin at the very basics and say, okay, what is a lattice? Okay, so the way you want to think about a lattice is, let's talk about, because lattices live in all different dimensions. So the picture I just showed you is actually a three-dimensional lattice. But now we're going to talk about one-dimensional lattices to begin with, because those are the simplest. So imagine you've got an ant and you're able to communicate with that ant. And you say to the ant, you can walk in a certain direction exactly 1 inch. All right, so here's the ant. It's a little blue blob. And you say to it, you can walk in the direction of the red arrow, and that's 1 inch. So that's a direction, and the arrow has a length. Okay. And you could do that forever, but that's the only way you can take steps. And so this is how an ant would take steps, right? And that's a one-dimensional lattice, okay? It's determined. So what that means is, to define it, all we needed was to give you a vector of a certain length. And the length of the vector tells me the length of the step that the ant can take, and the direction tells me the direction that the ant can take that step in. Right, what if I want to create a two-dimensional lattice? Well, I just need to specify 2 vectors, right? So here I've specified them to be at right angles to each other. Doesn't have to be. They could be at 60 degrees, 47 degrees, whatever, right? And they have, in this picture, they have 2 different lengths. So the ant can move up. Let's say the vertical arrow has length 1/2 inch, right? So it can move up. And it can take any combination of across and up, across and down, right? So you get this. So that's a two-dimensional lattice. It's specified by 2 vectors and their 2 lengths, right? And I just want to say that in real life, in reality, lattices are always finite, but mathematicians like to think of things as going off in all directions, all right? So this is an infinite lattice, okay? So now you've got this lattice, you can ask yourself, what symmetry? Okay, what can I do to this lattice that would keep it fixed? So I could move the whole lattice to the right by 1 step. And if it was infinite, it wouldn't move, it wouldn't change. I could move it up. So that's another translation. Perhaps I can reflect it. I can draw, I don't know if you can see my arrow, my cursor, but I could take any line, any vertical line, reflect this lattice in it, and I would get a symmetry. I could take any horizontal line, reflect it. I can also rotate it by 180 degrees. Okay, so there's one more thing I want to talk about, which is what's called a fundamental domain in mathematics. So it's a in this case it's a rectangle, and the idea about this fundamental domain is you can use it to create a tessellation. Okay, so you can translate that domain and create a coloring in solid yellow of this lattice in ways such that they don't intersect. But that's not the only fundamental domain. Here's another one. I could create a rhombus, okay? But once again, translates of that fundamental region will actually, fundamental region or fundamental domain will tile, okay? Okay, so we've sort of talked about the question of symmetry, and I've told you that we can talk about translational symmetry, rotational symmetry, we could talk about reflectional symmetry, and we haven't talked about permutation symmetry, and that's if I were to interchange, so let's go back to the chemists, they put atoms at each vertex of the lattice, and permutation symmetry is when you exchange them, okay? Okay, so we've seen fourfold symmetry, we've seen threefold symmetry, we've seen sixfold symmetry, right, in the emerald. But my question for you to think about, to mull over, while Charlotte is going to talk about tessellations, is can you create a two-dimensional tessellation, so she'll tell you what a tessellation is, which has fivefold rotational symmetry. And I want it to be a regular tessellation. All right, so Charlotte, it's all yours.
Thanks, Reem. Okay, so there's a few key words that sort of popped out of Reem's section there. One of them was tessellation. So some of you may have heard of this word before, some of you might be quite familiar, or the images on the screen might give you a bit of a hint. These are all taken from mosques and palaces inspired by Islamic geometry. So, sorry, dogs joining in. If you know what a tessellation is, please do add into the chat box, give us a little bit of a description of what you think a tessellation is. What do you think the rules are? What do you think these images all have in common? Most of these are taken from the Alhambra in Granada, which is somewhere you can go in south of Spain to see lots of these Islamic geometric patterns. And lots of mathematicians and geometrists like to travel there to go and see all these patterns. Sorry, can we have the next slide, please, Serene? So the rules of tessellations, which hopefully some of you have come up with, is that they have to be a repeating pattern with no gaps and no overlapping. These can be regular and these can be semi-regular. Next slide, please. Example of regular tessellations, they have to be made up of regular polygons. And again, the pattern has to be repeated, no gaps or overlaps. Whereas semi-regular tessellations, some of you may guess, are just involving two shapes. Actually, they can involve two or more regular polygons. So we've got a nice answer in the chat box as well here, shapes that fit together infinitely without an empty space between them. So that's a perfect definition of a tessellation. Thank you, Elliot. So semi-regular tessellations are very similar to regular tessellations. They have the repeating pattern. They're made up of regular polygons, but there's a little bit of an extra rule, and it's to do with the way that they come together. So it's quite subtle, but if you have a look at one of the vertices where all the shapes meet together, a semi-regular tessellation will have a repeating pattern. So for example, here we've got the yellow hexagon, we've got hexagon, square, triangle, square. Okay, and then it goes back to the hexagon again. And if we go to another vertex and we go to any vertex in this whole tessellation, it will be the same. So it will always, if you start with the yellow hexagon, it will always repeat the same pattern, hexagon, square, triangle, square. So we can call this a 6, 4, 3, 4 tessellation, because every vertex is the same pattern. Whereas there's a subtle difference with a demi-regular tessellation, which is where it looks at first glance like a semi-regular tessellation. You've got the same shapes, two hexagons, two triangles meeting at every vertex. However, the pattern is slightly different. So here we've got hexagon, triangle, on one of the vertices. And if we look at another one, also circled in red there, it's still 2 hexagons and 2 triangles, but they're in a different order. So we've got hexagon, hexagon, triangle, triangle. So there's a slight difference there. So what I would like you to do now, we're going to have a little bit of a time for you to actually do an activity. I would like you to explore regular tessellations. So I'm going to pop a couple of links in the chat box, on the YouTube chat box. So one of them is to an enriched tool, which allows you to explore tessellations. Okay, so if you open that up, the second one is a Padlet, which is basically where we're going to record our ideas. Okay, so on the Padlet, what I would like you to do is essentially write down anything that you spot. So what you're exploring here is which regular polygons can form regular tessellations. And if you feel like that's not challenging enough, you could have a look for a semi-regular tessellation, and you could even look for a demi-regular tessellation if you feel you would like a bit more of a challenge. If you open up the Enrich link, it will give you a tool to actually produce some polygons. So for example, you can fit together some triangles and see whether, as Elliot said, that they do fit together with no gaps and no overlaps, or whether there's any issues there. And then what I would like you to do on the Padlet is to write any ideas and thoughts you have. Now, as mathematicians, we come up with things called conjectures, which are things that we believe to be true, but we're still proving. Okay, so what I would like you to do is write down any conjectures you have. So it could be something like, I think decagons will tessellate in a regular way. Okay, now if you want to make it an even better mathematical conjecture, you can give a reason. So it might be as simple as, I tried it on the applet and it worked. It might be a bit more complicated. You might start thinking about angles, or you might start thinking about reasons why certain shapes will fit together and certain shapes won't. Okay, and it draws back to that question that Reem posed for you, which is, can you get a regular tessellation with fivefold? So perhaps thinking about pentagons there. Okay, so hopefully you've all managed to get your link open. I'll give you a few minutes to explore that together. If you don't have access to the enriched link, or you're perhaps watching as a class, you could explore this on paper as well. So you could try drawing some sketches to try and explain to yourself and justify to yourself perhaps why certain shapes might tessellate and why certain shapes might not. Okay. This is also something you can carry on exploring after the session. So the applet allows you to add lots of different types of shapes together and explore. You can also use a screenshot button or a snip tool if you've got one on your computer or your iPad or phone. And if you want to, you can actually upload some images onto the Padlet as well. So if you have some proof of your conjecture, you could paste that into the Padlet as well to show your reasoning. We'll leave the Padlet open as well after the session, so you can carry on working on it and you can carry on adding your ideas after the session. One thing you might be able to come up with is the number of regular polygons, the number of regular tessellations, which is more straightforward. Slightly more challenging but doable question is, how many semi-regular tessellations are there? So that might take you a little bit longer than we have in this session today, but you could see if you can find them all. So one of the ways that we like to work in maths is to exhaust all possibilities. So if you can find every single regular tessellation and every single semi-regular tessellation, can you convince us that there aren't any more? Why are there not infinitely many?
So Charlotte, I have a question. Can you, these semi and demi-regular tessellations, do you see them across history and in civilization? Do you see all of them being created by artists all over the world?
Yeah, so we're going to have a look a little bit later on about some of the places where you do find these tessellations. Actually, many of the Islamic geometric patterns, which we saw a few of those earlier, are based on regular and semi-regular tessellations as an underlying grid. Now, what's interesting about them, and one of the nice things about them, is that if it's considered to be a good piece of geometric art, you aren't supposed to be able to tell straight away what the underlying grid is. But if you unpick it, and you have people who specialize in pattern analysis, who sort of unpick all the artwork, you can identify underneath how the pattern started. And later on in this session, we're actually going to create part of a pattern that's based on fourfold symmetry, so based on a tessellation of squares. So giving you one away there, but I think most of you are probably happy that squares tessellate. You probably have them actually in your house, in your bathroom, in your kitchen, on the patio outside perhaps. So tessellations are often seen in tilings and in houses, in architecture, in artwork. So you probably have some examples in your, if you're in a classroom, maybe the floor tiles or the ceiling tiles are squares. Have a look around, see if you can see anything in your house or wherever you are today. There's lots and lots of examples, and there's also lots of near examples. So in nature, there's lots of things which look they might not be perfectly regular hexagons, for example, but you might recognize the pattern of a beehive, for example, as being a type of honeycomb, in a beehive, which has a very nice hexagonal shape to it. Okay, hopefully you've all had time to have a go at that. I'm going to just keep moving on, but yeah, got beehive pattern. Elliot's noticed that as well, thank you. So we'll just keep moving on. And what I would like to recommend is that you keep exploring these after this session. Some of you may have access to physical shapes that you can play around with, either at home, in your own toy box, or in your children's area. You might have some shapes at home, you might have some in your classroom if you're in school at the moment, or as I said, you can use the Enrich to keep exploring. Here are some examples of some student tessellations that were created at a workshop we did, and you can see that they've started to create some semi-regular tessellations there. One of the interesting things that comes up when you start making, particularly when you're looking at more complicated tessellations with many different shapes, is that sometimes it can look like it's going to work, but when you keep going, it breaks or it stops working, or you end up with a gap that you can't possibly fill with any of your regular shapes. And actually that goes back to Elliot's point, which is about it infinitely. So it has to work for the whole table if you're doing physical tiles, and it has to work for the whole screen if you're doing it on the computer. So do keep exploring that. And later on today, we're going to come back to regular tessellations. Next slide, please. And we're going to be drawing on this principle that most Islamic geometric arts are based on these repetitive grids. Okay, so you've got here two examples. So hopefully you came up with the three regular tessellations that are possible. We've already mentioned squares, again being something you probably see every day. Triangles, equilateral triangles are another one. Again, you may have seen these in, for example, windows. And sometimes it's used in kind of nettings and things like that. And we also already mentioned the honeycomb, which is another example of a regular tessellation, which is your hexagonal regular tessellation. So hopefully you identified that there are exactly 3 regular tessellations, and you may still be exploring how many semi-regular tessellations there are. Okay, so as I said, later on we're going to come back and we're going to actually do this one on the right hand side. We're going to create one of these stars, which is based on the fourfold symmetry, a fourfold regular tessellation of squares. And I'm back to Reem.
Okay, so when I left you, I asked you, can you create a regular tessellation with a regular pentagon? And the cat's out of the bag. No, you can't. But let's see why you can't. Okay, so first of all, let's see why you're allowed to have hexagonal tessellations, right? And the reason is because of the angle. Okay, the angle is a very nice angle. So if I created a hexagonal lattice, it would have to have 6-fold symmetry. And so what that means is I've got 2 vertices here. I've got this red vertex in the middle. So that means that that would be a center of rotation. If I rotated the lattice by 60 degrees, right, I should fix the lattice. So let's look at this blue point. Well, when I rotate it about this red vertex by 60 degrees, lo and behold, I will come back to a point which already exists in the lattice. And similarly, if I take this blue point as my center of rotation, and now I'm going to rotate in a clockwise fashion by 60 degrees, this red vertex, so I'm going to rotate it about this blue vertex. If I rotate that, that also lands on a point which is already in the lattice. Okay, so that's why you're allowed to create 6-fold tessellations, okay? But now let's see what would happen if we were to try and do that with a regular pentagonal tiling. All right, so if we could create such a pentagonal tiling, the first thing we'd say was, okay, let's pick 2 points. So I'm going to pick 2 vertices. So there's the red one in the middle here, and there's the blue one. And I've picked them to be minimal distance. Remember how you create a lattice? You can take a direction, a vector, and it's got a direction. So in this case, it's horizontal. And I know its length. So I've picked the one with the smallest length. All right. And I draw these 2 vertices, okay, that are closest together. Now, if this was a regular 5-fold symmetric lattice, then I could rotate it by 72 degrees, right? And that lattice should remain fixed. So I'm going to play the same game. I'm going to take this red point, red vertex. It's going to be my center of rotation, and I'm going to rotate in a counterclockwise, anti-clockwise fashion. And I'm going to ask myself, what happens to this blue vertex? Well, this blue vertex is going to go to this blue and red vertex, right? Now I can then take the blue vertex, blue and black vertex here, and rotate about it in a clockwise fashion. And so that red and black vertex is going to end up right there. And now there's a bit of trigonometry required, but basically you can show then that the distance between these 2 new vertices is actually less than the original distance between the 2 original vertices that I picked. All right. And that's a contradiction, because we took the first 2 vertices we took were actually at smallest distance possible. Okay. So there is a bit of trigonometry to actually make this proof rigorous, but that's how it works. That's why you can't have 5-fold symmetry, okay, in a regular tessellation. All right, so that is why when Daniel Shechtman discovered a crystal with 5-fold symmetry in 1983, he couldn't believe his eyes, right? So what he discovered, what he thought it was a crystal, but what he discovered was this crystal, its underlying lattice actually has some kind of 5-fold symmetry, all right? So therefore it can't be a lattice the way that mathematicians have defined it. Either that or mathematicians have been making a mistake for hundreds of years. So it was one of the 2, right? And in fact, when he discovered this, he talked to his line manager or something, and the line manager said, no, you know that can't happen. You can't have fivefold symmetry. Go back and find your mistake. Okay, but in fact, there was no mistake, and he got couple of decades later, he got a Nobel Prize for chemistry because of his discovery. All right, so what are these? These are what are called quasicrystals, and what are they? So I'll just show you first his a photo of his notebook when he made this discovery. So if you look at where my cursor is, he looked at an alloy of aluminium and manganese, right? So this is some kind of crystal and let's call it forbidden crystal or whatever. And he noticed that it had tenfold symmetry. Okay, so how did he see this tenfold symmetry? Well, he looked at a microscope. He looked at the object in a special kind of microscope, which will actually give you information about the lattice structure on which the atoms are arranged. All right. And so this lattice, whatever, I'm going to use the word lattice now in quotes, it had sixfold symmetry. So if you look at this picture on the bottom, okay, you've got sixfold symmetry, you actually have twofold symmetry. In fact, and then this picture, which I'll zoom in on in the next slide, if you count the dots around the central dot, you will actually see that there are 10 regularly spaced dots. Okay, so it turns out that the symmetries that Dan Shechtman could see in these quasicrystals were actually the symmetries of a regular icosahedron. All right, so that's this object here on the right, okay, which is still a regular shape. But what I want you to imagine is what would happen if you took this regular shape and you kind of like squelched it into 2 dimensions. What would you get? Okay, so here's a close-up of the picture. So now you can clearly count that there are actually 10 points around the central point. Okay, so that's the tenfold symmetry that Daniel Shechtman discovered. All right. Okay, so this is a photo of a quasicrystal. So objects that have this tenfold symmetry, or some symmetry that's not allowed by regular tessellations in 2 or 3 dimensions, because I should have said this earlier, not only can you not tessellate the plane with a pentagon, but you can't tessellate 3-dimensional space with a regular object which has 5-fold symmetry. All right. So most of these quasicrystals are man-made. All right. So the manganese aluminium alloy is a man-made quasicrystal. All right. As is this one. It's really tiny. Right. So the photo is taken with a 1-cent coin behind it. So that's like a 1p coin. And you can see it's quite small. Right. And you can also see that it has this kind of 5-fold symmetry. Right. There are some natural quasicrystals. There are a couple of them, and they were found in sort of meteorites which hit Earth, gazillions of years ago. But they do exist in very, very small quantities. Okay. All right. So it turns out, so the chemists found actual quasicrystals in the 80s. Mathematicians like to talk about models of objects that exist in real life. All right. So it turns out that Sir Roger Penrose had found a 2-dimensional tiling, tessellation, which is not regular, right? So it's a tiling of 2-dimensional space using 2 shapes, but this tiling is not regular. All right. So he was looking for some kind of local 5-fold symmetry. So he picked 2 parallelograms. All right. So there's the red one, which has 72-degree angle, which, by the way, in fact, is kind of pentagonal. The pentagon has angles of 72 degrees. So that's one thing there. And he picked another parallelogram, which had a 36-degree angle as its acute angle. And then he said, well, what can I do with these? Can I tessellate the plane? Okay, or can I tile the plane? Well, it turns out you can, and it's really boring. Okay, so here, if you were to cut these 2 pieces of these 2 shapes, and in a minute you will see that you can, because we've put it on the drive, you will have access to this. You can cut them, many copies of the red one and the yellow one. You can actually fit them together to get a regular tiling. All right, and at the bottom left-hand corner here, these 2 arrows, those are the 2 vectors with which you can define your lattice. Okay, and the purple hexagon that I've colored in, that's one of the fundamental regions that I talked about earlier. So you can tile the plane with that, with translates of that fundamental region, and there will be no holes, right? So this was, Penrose was a little bit underwhelmed by this because he actually wanted something a bit more interesting, and he wanted something with fivefold symmetry and clear, sort of local fivefold symmetry. And clearly this thing does not have fivefold symmetry. So what he decided to do was he went back to his two shapes and he put markings on the edges, all right? Now, in the shapes that you can cut out, you can do this in many different ways. You could put markings on the edges, so you can actually, put double arrows on some of the edges and single arrows on some of the other edges. And the rule is you can put these pieces together as if you were in a jigsaw puzzle. But if you're going to put two edges next to each other, their arrows must align, right? So you can't have a single arrow edge stuck next to a double arrow edge, and they must go in the same direction as well, the arrows, all right? So when you do that, with that constraint, it becomes a lot harder to tile the plane, but in fact, you can tile the plane, all right? And this is an example of the beginning of a tiling, right? Which will eventually cover, remember, mathematicians like infinity, so we have to go to infinity in all directions, which will actually expand to tile two-dimensional space, all right? Now, if you look at this picture, all right, I'm going to say some things about it. The first thing you see is you do see fivefold symmetry, okay, because you've got this flower in the middle, and that's a flower with 5 petals, right? So you can rotate locally, and that shape, that flower would actually be fixed under a rotation, right? But in fact, if you were to rotate, this is the thing you have to get your head around. If you were to rotate by 72 degrees, although that flower in the center, this thing here, would be fixed, as you move outside towards the edges of the page, and as you complete this tessellation or this tiling, you will actually not get complete fixation of the vertices, all right? So there will be some pieces which don't align, okay? And that's a quasicrystal. A quasicrystal in mathematics is something which locally, so if you were to zoom in and just look at the middle, you'd say, oh yeah, well, that's clearly regular, right? That's clearly a regular tiling where things just repeat in both directions, up and across, right? But in fact, if you zoom out, you will see with good enough eyes that there are places where the fivefold symmetry is not going to actually be respected, all right? And those lattices, all right, so this lattice, this Penrose tiling, if you do the mathematics, and there's a lot of mathematics involved, its symmetries are like the symmetries of the quasicrystal that Shechtman discovered, all right? Okay, so this is a photo of a wood jigsaw puzzle that's made with these tiles. So remember I told you you can have different markings. So in the picture I showed you, we had put arrows on the edges. Here, what they did was, instead of having arrows, they sort of turned the edges into these curved spaces, curved lines, right, that have to fit in together, right? And in the puzzle that you can download, print out, and cut up, and I suggest you cut up lots and lots of them, okay? I think you have curves inside the tiles, right? And you have to do it in such a way that the curves aren't broken and you make these nice loopy paths, okay? Just want to tell you one more thing, that when you start putting the pieces together, you will often, it's actually what Charlotte said a minute ago, you will often put them together, and then there's going to be a place where there's a hole which you can't fill. And then you have to start all the way at the beginning again, or maybe undo a few of them and see if you can fill them up in a way. But there are, no matter how large a patch you want to create, so this is a patch, right? It's like a finite part of the Euclidean space that I've tiled, okay? No matter how hard, no matter how big a patch, you can always create one, okay? So if you run into a hole, it means you did something wrong. All right, and here is Sir Roger Penrose on his tiling. So this is at the Mathematics Institute in Oxford, and they've tiled the floor with some of his Penrose tiles. Okay. Okay, so to actually understand the mathematics, so I'll just talk a little bit now about the mathematics, but to actually understand the mathematics, this is two-dimensional space, which is a model for the quasicrystals that Dan Sheckman saw, which were in three-dimensional space. So to actually understand it, you have to start all the way at the beginning in one-dimensional space. All right. So this brings us back to, can we create an aperiodic tiling in one dimension? All right. So a tiling which is not regular, right? So it's going to be created by two vectors, in fact, but they're in one dimension. Okay. So the simplest one uses the Fibonacci sequence. Okay. So let's remember how, or if you haven't seen it, let me tell you about the Fibonacci sequence, which was known to Fibonacci, right? This Italian a long time ago. So in fact, I can't remember, is it the 12th century or the 13th century? Don't quote me on that, okay? So how do you create the sequence? So you have an adult rabbit, all right? And that adult rabbit lays a baby rabbit every day, right? So it lays a baby rabbit, okay? And now there are two rabbits. There's an adult rabbit and there's a baby rabbit. Now, what happens is that the baby rabbit takes them one day to grow up to become an adult rabbit. So the next day, how many rabbits do you think there will be the next day? Well, this rabbit, the adult rabbit, will have another baby, and this baby rabbit will actually have grown up. So we're going to have 3 the next day. Okay. How many are we going to have the day after? So remember, the adult rabbits will have a new baby, and the baby rabbits will become adult rabbits. So I will tell you how many they're going to be. They're going to be 5, right? Because this adult is this adult. It has a baby. This baby grows up. This one, who's a grown-up, is there and has another baby, right? And I can keep going. And now, if you count the rabbits, okay, you will see that there's 1 the first day, 2 the second day, 3 the third day, 5 the 4th day. And if you think carefully, on the 4th day, how many rabbits are there? Well, all the rabbits that were there on the 3rd day come down. And because there are 2 rabbits on the step before, they both are grown up, so they have 2. They're both grown ups at this stage, so they have 2. They bring down 2 more, right? So to get the number of rabbits on any one day, you have to add up the rabbits on the previous day and the rabbits on the day before that. Okay. All right. But this is already quite complicated because we're distracted by the rabbits. Maybe you think they look cute. We don't want to distract you. We're going to be mathematicians. And we're going to say the grown-up rabbit is a 0 and the little rabbit is a 1. Okay. And then this picture where I've put hint rabbits, because I haven't asked the question yet, is I've just redrawn the picture with the rabbits, but every grown-up rabbit is a 0 and every little rabbit is a 1. So I think you might think this is a lot less exciting, but it encodes all the information in the other picture. And then my next question would have been, what are the next 8 entries as you keep repeating this? Okay, what are you going to replace 0 by? Well, 0 gets replaced by 0, 1. And 1 gets replaced by 0 because the little rabbit becomes a grown-up rabbit. Okay, so here's the grown-up rabbit. It turns into a 0 and a 1. In fact, I've got this on the next page. Okay, so the grown-up rabbit becomes grown-up plus child, and the child becomes a grown-up. So every time I see a 0, I replace it by a 0, 1. And every time I see a 1, I replace it by a 0. And I keep repeating this from day 1 to day 2, day 2 to day 3, and so on. And this gives me something that I can program into the computer to generate my population of rabbits on the nth day. Okay, so here, this is first day, second day, third day, fourth day, fifth, sixth, seventh, and eighth. Okay. And so we can take this whole thing. I think I'm running out of time, but we can take this whole thing and we can actually turn it into a tiling. So I'll just tell you that this yellow tile is now going to replace the grown-up rabbit, right? And the green tile, which is short, is going to replace the baby rabbit, all right? The Fibonacci numbers are somehow related to this amazing number called the Goldine ratio, which the ancient Greeks knew. It's the most magnificent number ever, because if you get what's called its continued fraction expansion, it's highly symmetric. Okay. And what happens is the large bunny having a baby means that sort of it grows up, it gets larger, and then you cut it, and then you have a big rabbit followed by a little rabbit, and the little rabbit becomes large. And this picture will end up being a tiling of one-dimensional space, all right, which it's tiling of one-dimensional space by two objects, which is sort of has some kind of symmetries, but is not a regular tiling. Okay, so that's how you get one-dimensional tiling, and the Penrose tiling is how you would get a two-dimensional tiling. And there are mathematicians who study this in the field of what's known as aperiodic order, and it actually uses some very complicated mathematics. I think that's all I have time for, right, Charlotte? So I'm going to transfer you. I'm going to leave these slides. If you're interested, you can go back, download these slides, and answer the questions that are in those. But at this point, I'll go back to Charlotte.
Thank you, Reem. Yeah, it's a fascinating topic, and actually, we have recently had an exhibition in Milton Keynes, which displayed a lot of the aperiodic artwork that can be created based on these patterns that Reem was talking to you about, including the Penrose tiling. We also had some regular tessellation work, lots of Islamic geometric inspired artwork, and the link to our online gallery is actually in the chat box. So it says you can see some examples of student work in our gallery. So if you want to have a look afterwards and keep exploring, you can have a look at our online gallery. And excitingly, we also have another in-person exhibition in the National Museum of Scotland on Sunday this week. So there's information on the Maths Week Scotland website. If you're in Edinburgh or close by and you want to go along, you can see lots of this lovely artwork. Now, speaking of lovely artwork, we are going to create something ourselves now. So in a moment in the chat box, there is going to be a link to a Desmos page. And on the Desmos page, you are given a blank octagon on the left-hand side, and you are given an 8-pointed star on the right-hand side. And the idea is that we are going to create our own 8-pointed star. Okay, so this pattern here that you can see on the screen is a very popular motif found in Islamic geometric art. You can see here, this is a set of ceramic tiles, wall tiles, but it's also found in lots of paintings, tapestries, wood carvings, all kinds of places. It's a very popular kind of 8-pointed star and cross motif. So what we're going to do is we're going to create the star. So on the next slide, you'll see what we're going to be creating, which is this pattern here. Okay, so you can see it's an 8-pointed star, but it's got this lovely decoration on the inside. So on Desmos, as I said, you're given the template, which is an octagon, and the challenge to make it mathematical and not just a kind of instructional process. I want you to try and work out how to get from one to the other. So you've been given an octagon, which I'll give you one clue. I'm not sure, Reem might have to move the cursor for me, but if you move from around each of the vertices in a straight line, you would actually get an octagon. So just the outside points of the star, sorry. So the outside points of the star, if you joined up the outside points of the stars with a straight line, then you would get an octagon. Yes, exactly like that. So that's your starting point. Okay, so your 8-pointed star is going to sit inside that octagon. Okay, now you need to think about which straight lines you want to add. Now, I recommend on Desmos that you use the straight line tool, not the kind of freestyle pencil tool, because it will make it a lot easier for you. So what you're going to do is try and work out which of the vertices of the octagon you need to join up in order to make this star. And one of my clues is that you will have some extra lines that perhaps you need to rub out. Okay, so you might be able to, if you look at this 8-pointed star, you might be able to see that it's actually, if we just focus on the outside to start with, it's actually made of 2 overlapping shapes. Maybe you can work out which shape it is made up of. Okay, so it's one of the shapes we've met today. It's a regular polygon. 2 overlapping shapes will give you the outside of the star. Then you might have to think about getting rid of some of the extra lines that you don't want. And then once you've got your outside star, you can start looking at some horizontal and vertical lines and some diagonal lines that might help to get that little inner star. Okay, so again, using your problem solving, your mathematical observation skills, you're going to be joining up those points to make your star. Okay, and you can do this on Desmos. If you don't have access to Desmos right now, Reem has already mentioned that we have a Google Drive with lots of resources in there. In there is also an octagon that you can print out. So you might like to do it after the session on paper instead. One of the advantages of doing that is that you can make lots of them and you can put them together to make a lovely tessellation picture, which I'll show you in just a moment. But if you do manage to make your own star either on Desmos or on paper, we have another Padlet for you, which is about to be shared in the chat. And on that Padlet, you can actually upload your star, your picture, and share it with everybody else who's working there today. There are some examples up there of some stars that have already been produced and some pictures. If you don't finish a star but you want to do some research online and find one, then you can also paste that up onto the Padlet for us to look up. So hopefully you're all having a go at that on Desmos. If we look at the next slide, I'll show you what I was talking about if you do this on paper. So here's an example of some students at the Royal Institution who I worked with, who we did this on paper. They each produced their star using just a ruler and pencil, and then decorated themselves. And what's really nice about this is that you can create a piece of collaborative artwork. So this could be something you do just by yourself at home, or it could be something you do with friends or classmates. Each make a star, pop it together to make this pattern. Now, strictly speaking, it's not a tessellation because there are gaps, but if you use your imagination and you use a nice piece of colour backing paper, you can see that what's left in the gaps is this lovely cross shape. So your stars, if they meet together at the kind of horizontal and vertical points, then you end up with this lovely Islamic cross in the middle. You get this lovely pattern of the stars and crosses. So yes, we're slightly running towards the end of the session, but the nice thing about this activity is that you can carry on in your own time. In fact, I recommend that you do, because it gives you more time to sort of decorate and beautify these stars. Either on Desmos, there is a colouring in tool. It's fairly basic, but you can get some nice colours on there, or printing out the template and having a go yourself. And if you are a class or a group of people doing it, if you all print out the same template, you'll end up with the same size stars, and they'll fit together perfectly to make this pattern. Just to wrap up this activity, I'm going to talk to you about a few resources that are available for you, which I think is on the next slide. So one thing is that if you are particularly interested in this Islamic geometry, then I can recommend an artist who produces YouTube videos which teach you how to create these from scratch. Her artwork is actually behind me here. Got one of her pieces in my House, that you can look on her YouTube channel and find out more about how to create these from scratch. These slides are available for you with all the links in the Google Docs folder, which I mentioned. So we'll get that over to you now in the box. So you can carry on after this session, and you can look at the YouTube video, you can create your own pattern. And as Reem mentioned before, there's also a Penrose puzzle for you to have a go at. And once you've created your Penrose puzzle, you may also like to decorate that and make that into a nice piece of geometric artwork. Okay, so just wrapping up on the final slide. As I mentioned, we've got these resources for you. We've got the art gallery for you to have a look at. You can see some examples of some student created Penrose tilings as well on the gallery. We would love you to share with us anything that you create. So please do share with us on the Padlet that we've sent you. And finally, I'm just going to ask in the last few minutes if you could please fill out the feedback form, which I'm just going to paste now into the chat box, to let us know what you enjoyed and anything we could do better for next time. And finally, I will also give you some links to some other materials that you might like to look at, which are not linked to this session, but we have some games for you available on OpenLearn to do with more puzzling mathematics. So we've got a Perplex problem solving puzzle app, and we've also got a code breaking app which we launched at Maths Week Scotland last year. So please do have a look at those and keep exploring some fun maths. And we hope you enjoyed this session. Thank you very much.
Yeah, thank you for listening, and we really do hope that you click on all the links and cut out all these shapes and make some fabulous patterns and get interested in the mathematics behind it. All right, thank you.
Thank you.